In the vast quiet of the cosmos, our galaxy sails silently through space, a shimmering spiral adrift in an ocean of stars. The Milky Way, for all its brilliance, is just a speck among countless others. And yet, this speck is not standing still. Long ago, astronomers noticed something strange. Our galaxy is moving, not spinning in place, but drifting, pulled by unseen forces. It is as if we are caught in a slow but unstoppable current, drifting through a universe that never rests. We often think of space as a static backdrop, where planets spin, stars burn, and galaxies glow in their eternal positions. But that is an illusion. Everything moves. The Earth spins on its axis. It orbits the Sun. The Sun, in turn, follows a sweeping path around the center of the Milky Way. And the Milky Way itself? It is being drawn, dragged even, towards a mysterious location in the sky, toward a region cloaked by our own galaxy's dust, invisible to ordinary eyes. Astronomers gave this hidden place a name, the Great Attractor, a title as poetic as it is ominous. They could not see what was there, but the motion was undeniable. Every galaxy in our neighborhood, dozens, then hundreds, seemed to be heading the same way. It was not just gravity from nearby objects. It was something bigger, something that seemed to reach across millions of light years, pulling on the Milky Way and everything near it. Imagine drifting on a raft in the middle of a dark ocean. There are no stars above, no landmarks around, only the feel of the current beneath you. You are moving, but you do not know where or why. That is the position we find ourselves in. For most of human history, we believed we were still, that the universe spun around us. But the deeper we look, the more we discover. The universe is restless. Motion is not the exception. It is the rule. This motion is not always obvious. We do not feel it beneath our feet. We do not hear it in the silence of space. But it is there, written in the glow of ancient light, mapped in the trajectories of distant galaxies, and whispered in the gentle warmth of the cosmic microwave background. It is in the physics of space-time itself, and in this episode, we will follow that motion, from the Earth's rotation to the Sun's journey, from the pull of the Great Attractor to the farthest reaches of cosmic destiny. It was in the early 1970s that astronomers began to uncover a cosmic mystery that would challenge everything we thought we knew about our place in the universe. Observations at the time suggested that the Milky Way galaxy, along with many of its neighbors, was not simply floating in space, but moving, being drawn towards something enormous and unknown. A gravitational pull, immense in scale and invisible to telescopes, was acting on entire clusters of galaxies. But what was causing it remained a mystery, hidden behind the dense plane of our own galaxy. This region of obscurity, known as the Zone of Avoidance, lies along the plane of the Milky Way and is filled with thick clouds of gas and dust. It blocks our view of what lies beyond it, making it difficult for even the most powerful optical telescopes to see through. And yet, something behind that veil was exerting its influence, pulling entire galaxies in a shared direction. It was as though a hidden mountain was shaping the flow of a great river, bending space and motion without ever revealing its true form. Two astronomers, R. Brent Tully and J. Richard Fisher, were among the first to glimpse this grand movement. Using the Parkes radio telescope in Australia, they set out to measure the velocities of distant galaxies. Their goal was to chart the large-scale structure of the cosmos. But what they found was even more extraordinary. Galaxies separated by millions of light-years appeared to be moving in roughly the same direction. Their motions, when reconstructed, all pointed toward a common locus in the sky, toward the zone of avoidance. At the same time, other astronomers were studying the cosmic microwave background, the afterglow of the Big Bang, a bath of ancient radiation that fills the universe. This background is remarkably uniform, but not perfectly so. It is ever so slightly warmer in one direction and cooler in the opposite. That difference, known as the dipole anisotropy, is a clue to motion. It reveals that the Earth, the Sun, and the entire Milky Way are moving with respect to this ancient light. Even after accounting for the motion of our solar system within the galaxy, a residual speed remained, several hundred kilometers per second, in a specific direction. Together, these two lines of evidence, galactic motion and cosmic background radiation, pointed to the same conclusion. There was a massive gravitational source beyond the Milky Way, one that could not be seen directly, but whose presence was written into the sky itself. The galaxies were not simply drifting through the universe. They were falling towards something vast and powerful. Unable to identify the object, astronomers gave it a name that captured both its mystery and its might: the Great Attractor. For decades, that name was all we had. We could not map it, we could not see it, and we could not fully explain the speed and direction of the galaxies it influenced. It was a ghost embedded in gravity, a whisper in the background noise of the cosmos. But it was real. And as more data arrived, it became clear that this great attractor was only a part of an even larger story, one that stretched across hundreds of millions of light-years and involved not just our galaxy, but the entire local universe. This was only the beginning. For most of human history, we believed that the Earth was the center of everything. The sun, the moon, the stars, they all appeared to rise and set around us in perfect, clockwork motion. It made sense, and for a time, it worked. Ancient astronomers devised complex models to track the movements of celestial bodies, embedding circles within circles to explain their paths. But these models were built on a fundamental assumption: that the Earth was still, unmoving, anchored at the center of the universe. It would take centuries to unravel that idea. In the mid-16th century, the Polish astronomer Nicholas Copernicus proposed a revolutionary shift. In his model, it was not the Earth that sat still, but the Sun. The Earth, he argued, moved, rotating on its axis and orbiting the Sun. It was a bold claim, and at first, deeply controversial. After all, if the Earth truly moved, why did we not feel it? Why were we not flung off into the void as it spun and raced through space? It would take the laws of motion and gravitation, discovered more than a century later by Isaac Newton, to explain why we can move at great speed without even noticing. Today, we know that motion is everywhere. The Earth spins at over 1,000 kilometers per hour at the equator. It travels around the Sun at roughly 30 kilometers per second. The Sun itself orbits the center of the Milky Way at over 200 kilometers per second, completing one revolution every 230 million years. These motions layer upon one another, creating a complex, ever-shifting dance through space. And yet, we feel none of it. To us, the Earth feels still, not because it is motionless, but because we are moving with it. Motion in the universe is relative. That was one of Albert Einstein's great insights. There is no absolute frame of reference, no cosmic ruler or fixed point from which all motion can be measured. Instead, every object moves in relation to something else. You can sit on a train and watch the world go by, or stand on the platform and watch the train rush past. Both perspectives are valid. In space, this principle holds true across all scales. A galaxy can be still in one frame and hurtling in another. What matters is what it is moving relative to. But the universe gives us a special tool, a kind of universal reference frame. Because the cosmos is expanding, galaxies are, on average, moving away from each other over time. This expansion defines a cosmic flow, a general outward movement. Any object that deviates from that flow by moving faster, slower, or in a different direction has what cosmologists call a peculiar velocity. It is a way of defining motion not just by relative position, but by comparing it to the large-scale behavior of the universe itself. This idea is critical because it allows us to track not only the motion of the Earth or the Sun, but also the journey of the Milky Way within the broader cosmic landscape. From our vantage point, we may seem still, but measured against the cosmic microwave background, the afterglow of the Big Bang, we are moving, undeniably, inexorably, hundreds of kilometers per second, drawn by gravity, propelled by ancient interactions. This is the true nature of the universe. Not a quiet stage where matter rests, but a restless, dynamic arena where everything is going somewhere, even if we do not yet know where. It may be difficult to grasp, but you, yes, you, are moving through the universe at astonishing speed. Right now, even as you sit still, you are hurtling through space on a spinning planet that orbits a star which itself is journeying across a galaxy. You may not feel it, and nothing in your daily experience betrays this truth, but your life is a voyage through the cosmos. Every heartbeat, every breath, happens while you are in motion. And over the course of a lifetime, the distances you travel are nothing short of cosmic. Begin with the most familiar motion, the rotation of the Earth. The planet spins once every 24 hours, and depending on where you live, that spin may carry you at speeds of up to 1,600 kilometers per hour. At the equator, that velocity is at its maximum. Closer to the poles, it slows until it reaches zero at the very top and bottom of the planet. Most people live somewhere in between, traveling at speeds around 1,000 kilometers per hour without even noticing. Then consider the Earth's orbit around the Sun. Every year, our planet traces a nearly circular path around its star, covering a distance of nearly 1 billion kilometers. To complete that journey, Earth must move at an average speed of about 30 kilometers per second, roughly 108,000 kilometers per hour. That means that, over an average human lifetime of 80 years, each of us travels more than 80 billion kilometers, simply by orbiting the Sun. But the journey does not stop there. The Sun itself is also on the move, orbiting the center of the Milky Way galaxy. This path is far grander, taking more than 200 million years to complete a single revolution. During that time, the Sun races through space at approximately 230 kilometers per second. Along for the ride are all the planets, asteroids, comets, and clouds of dust that make up our solar system, including us. If you lived long enough, you would one day return to your current position, but only after traveling billions upon billions of kilometers around the galactic core. And the Sun does not follow a perfectly flat path. It gently bobs up and down through the thin disk of the Milky Way, rising and falling like a cork floating in dark water. This vertical motion is shaped by the gravity of the galaxy, tugged here and there by the collective pull of billions of stars. Right now, we are passing through a region known as the local bubble, a vast cavity in the interstellar medium, likely carved out by ancient supernova explosions millions of years ago. Its density is so low that, on Earth, it would register as a vacuum. So, what does it all mean? It means that, without taking a single step, you are constantly in motion. You have always been moving. And by the time your life comes to a close, you will have traveled distances beyond your imagination. Billions upon billions of kilometers across spinning worlds and orbiting stars. You are not a fixed point in space. You are a traveler, an unconscious explorer, riding the currents of gravity and time through the restless fabric of the universe. And that journey has only just begun. As the Sun follows its grand orbit around the center of the Milky Way, one simple but profound question emerges. What keeps it in place? Moving at hundreds of kilometers per second, the Sun should, by all accounts, have escaped the galaxy long ago. Its tremendous speed ought to fling it into intergalactic space, and yet it does not. It remains bound, circling in a stable path, tethered to the invisible mass of the galaxy. But when astronomers tally up all the stars, gas, and dust within the Sun's orbit, The numbers do not add up. There is not nearly enough visible matter to account for the gravitational force holding us in. This is where one of the greatest mysteries of modern cosmology enters the story: dark matter. It neither emits nor reflects light. It cannot be seen directly, but its presence is undeniable. It exerts gravity, it shapes galaxies, and it surrounds us. Based on the rotation speeds of stars and galaxies, including our own, scientists estimate that dark matter must outnumber visible matter by more than 5 to 1. In the case of the Milky Way, it forms an enormous halo, extending far beyond the spiral arms and disk, enveloping the galaxy in a ghostly shell of mass we cannot see. Without this dark matter halo, the Sun would not be orbiting, it would be escaping. The speeds we observe would be impossible to sustain with only the visible matter to hold things together. And so, dark matter is the glue that keeps our galaxy intact. It is the silent architect of the Milky Way's structure, a gravitational scaffold that has shaped the fates of stars and solar systems for billions of years. We owe our place in the galaxy to this unseen material, whose nature remains one of the deepest open questions in physics. Yet the Sun's motion is not purely circular. As it orbits the galactic center, it also rises and falls, oscillating through the thin plane of the galactic disk over tens of millions of years. This vertical bobbing is the result of gravitational perturbations from nearby stars, gas clouds, and clumps of dark matter. Like a boat riding long, slow ocean swells, our solar system experiences gravitational tides as it weaves through the galaxy's structure. These motions, though subtle, reveal the dynamic environment of interstellar space. At this very moment, the Sun is traveling through an unusual region known as the local bubble. This bubble is not made of soap and water, but of nearly empty space. It is a cavity about 1,000 light-years across, carved into the interstellar medium by a series of ancient supernovae. These titanic explosions, which marked the deaths of massive stars, blasted out shockwaves that swept up gas and dust, leaving behind a vast volume of hot, low-density plasma. The local bubble is so diffuse that by terrestrial standards, it would qualify as a better vacuum than any ever created in a laboratory. Our solar system likely entered the local bubble between 5 and 10 million years ago, and we are still passing through it. The boundary of the bubble is not sharp, but formed by denser walls of gas and dust swept outward by the shock waves. Inside the bubble, the conditions are different than the typical galactic environment. Radiation propagates more freely. Interstellar particles are scarcer. And recent studies suggest that the local bubble may be influencing everything from the shape of the heliosphere, the bubble of solar wind surrounding our system, to the paths of cosmic rays reaching Earth. Taken together, these facts paint a striking picture. We are not only orbiting and spinning, we are drifting through remnants of ancient stellar violence, surfing waves of gravity created by invisible matter, and wandering through a region of space shaped by cataclysm. This motion is not random. It is written into the structure of the galaxy itself, a record of star formation, destruction, and interaction over billions of years. The local bubble, dark matter, and the sun's path through space are not isolated curiosities. They are part of a single, continuous story. The restless journey of our solar system through the ever-evolving landscape of the Milky Way. Look up into the night sky, and there, just above the horizon in the northern hemisphere, lies a faint smudge of light, easy to miss, but impossible to forget once seen. This is the Andromeda galaxy, our nearest galactic neighbor. For centuries, it was thought to be just another nebula, a cloud of gas within our own Milky Way. But in the early 20th century, the American astronomer Edwin Hubble proved otherwise. Andromeda was not part of our galaxy. It was another galaxy entirely. An island universe in its own right, containing hundreds of billions of stars and sitting over 2 million light-years away. At first, it seemed distant and unthreatening, a celestial wonder quietly shining from afar. But Andromeda is not static, it is moving. Unlike most galaxies that recede from us due to the universe's expansion, Andromeda is one of the few that is approaching. It is heading straight for the Milky Way. This was confirmed not through photographs, but through spectroscopy, by analyzing the light from its stars. That light is slightly shifted toward the blue end of the spectrum, a clear signature of motion toward us. And in 1957, Dutch astronomer Hendrik van de Hulst measured that speed to be nearly 300 kilometers per second. But motion is more than just forward or backward. For decades, astronomers lacked a complete picture of Andromeda's trajectory. Did it only appear to move toward us while actually sliding past sideways? Or was it truly on a collision course? It was not until 2012, when the Hubble Space Telescope tracked thousands of stars within Andromeda, that we got our answer. The galaxy is heading directly toward us, and a collision is inevitable. This slow-motion crash will unfold over the next several billion years, and it will reshape the night sky, our galaxy, and perhaps our understanding of cosmic fate. In just over 2 billion years, Andromeda will begin to grow in our sky, becoming the most dominant object we have ever seen. At first, it will resemble a glowing smear, like a fist held at arm's length. But with each passing epoch, it will expand, its spiral arms stretching wider, its core glowing brighter, until it spans the sky, thousands of times larger than the full moon. The gravity between our galaxies will begin to tug at their stars, drawing out long tidal tails, like bridges of starlight arcing across space. The dance will begin. But this will not be a violent crash in the way we imagine car accidents. Galaxies, despite their name, are mostly empty space. The average distance between stars is so vast that direct collisions between them are rare. Instead, they will pass through each other like swarms of bees, with stars weaving past one another in a silent ballet. But while individual stars may not collide, their orbits will be torn apart. Gravitational encounters will fling some stars into the darkness, exiling them forever from any galaxy. Others will fall inward, settling into new chaotic paths. This gravitational turbulence will compress clouds of gas and dust, triggering waves of star formation. For a brief moment in cosmic time, the night sky will blaze with the birth of countless new stars. Young, hot, blue stars will light up the sky, and their brilliance will illuminate the tidal bridges and twisted arms of the two galaxies. It will be a time of renewal and chaos, a final blaze of activity before the fire burns out. Because even as the galaxies merge, their supplies of gas will begin to run low. The fuel for starbirth is finite. After the initial collision, the galaxies will drift apart slightly, only to be pulled back together again. This cycle will repeat several times over hundreds of millions of years, each pass drawing them closer until they finally coalesce. In the end, what emerges will not be a spiral galaxy like the Milky Way or Andromeda. It will be a giant elliptical galaxy, rounder, redder, and quieter. Astronomers have already named it Milkomeda, a hybrid of the two titans that birthed it. By that time, our sun will have long since burned out, leaving behind a cold white dwarf. But if Earth, or anything like it, still exists, the sky will be forever changed. Gone will be the familiar constellations, the well-known stars that guided human civilizations for millennia. In their place, an unfamiliar tapestry of light, brighter, wilder, and more chaotic, and then, gradually, dimmer. With little gas left to form new stars, Milkomeda will age into silence. The young blue stars will die quickly. The older, red stars will fade, and the galaxy will grow still, a vast, glowing ember in the darkness, drifting alone through the universe. The collision, for all its brilliance, will mark not just a transformation, but a slow descent into cosmic quiet. The merger of the Milky Way and Andromeda is not a catastrophe, it is a continuation. Galaxies have collided and merged since the earliest epochs of the universe. This is how structure forms. This is how growth happens. We are witnessing the future, written in the mathematics of gravity. And in that future, we are not standing still. We are part of something larger. Two galaxies, once strangers across the void, now set on a path toward union. It is not an end, it is a beginning. One shaped not by violence, but by motion, endless, graceful, and unstoppable. The Milky Way and Andromeda are not alone in the cosmic wilderness. They are the two largest members of a gravitationally bound collection of galaxies known as the Local Group. This group contains more than 50 galaxies, most of them small and faint, dwarf galaxies that quietly orbit the giants. Triangulum, the third largest, may one day join the Great Merger, adding its mass to the growing galactic core. But beyond this local neighborhood, the story continues. The local group itself is not isolated. It too is moving, drawn towards something even larger. That next level of structure is the Virgo cluster, a dense and massive collection of over 1,000 galaxies located roughly 55 million light-years away. From the edge of the local group, Virgo is like a great gravitational sink, pulling galaxies and groups into its embrace, and we are among them. The local group is not only heading toward Virgo, it is falling into it. Slowly, inexorably, the pull of gravity is shaping the paths of entire galactic communities, bending them toward a common center, like leaves spiraling into a drain. For decades, astronomers thought the Virgo cluster was the heart of our larger cosmic region. They referred to this region as the local supercluster, a loose collection of groups and clusters stretching over 100 million light-years. But this picture was incomplete. It was based solely on where galaxies were located, not where they were going. It lacked motion. It lacked direction. And then, in 2014, something changed. Astronomer Brent Tully and his colleagues applied a new approach, one that traced not just the positions of galaxies, but their peculiar velocities. They asked, what if we mapped the cosmic flow? Using data from thousands of galaxies and a mathematical technique known as the Monge-Kantorovich reconstruction, Tully's team tracked the motions of galaxies over cosmic time. Instead of seeing a scattered web of stars, they saw rivers, currents of galaxies flowing toward common destinations. The result was stunning. What we had once considered a supercluster was revealed to be merely one branch of a much larger structure. 4 branches in total, each containing thousands of galaxies, all converging toward a single gravitational center. This was not just a supercluster, it was something grander. They named it Laniakea, a Hawaiian word meaning immense heaven or open skies. It is a fitting name for a structure of such scale. Laniakea spans over 500 million light-years and contains more than 100,000 galaxies. At its heart lies the Norma cluster, the same gravitational source long suspected to be the Great Attractor. But Laniakea is not a rigid object. It is a living flow of galaxies, collapsing slowly over cosmic time, forming the scaffolding for future mergers, collisions, and transformations. In this vast hierarchy, the Milky Way belongs to the local group. The local group is part of the Virgo branch. The Virgo branch flows toward the center of Laniakea. And so we are part of a chain of motion, galaxies within groups, groups within clusters, clusters within superclusters, each scale connected by gravity, each motion part of a greater whole. From our tiny solar system to the immense sweep of Laniakea, the universe is not a static tapestry. It is a dynamic, ever-evolving symphony of movement. And yet, even this may not be the end. Recent observations suggest that Laniakea itself is being pulled toward an even larger structure, the Shapley Supercluster, far beyond the reach of our current maps. The deeper we look, the more we realize there is always another scale, another center of motion, another horizon yet to be reached. The journey of the Milky Way is not confined to a single galaxy, or group, or cluster. It is a voyage across cosmic architecture, carved by gravity and unfolding over billions of years. At the heart of Laniakea lies something strange, something we cannot quite see, but which leaves its mark on the motion of galaxies across hundreds of millions of light years. We call it the Great Attractor. It is not a single galaxy or black hole, nor is it a bright, burning quasar. In fact, it is not directly visible at all. It sits behind the thick clouds of our own galaxy's disk, in a region known as the Zone of Avoidance, a patch of sky so obscured by gas and dust that optical telescopes cannot pierce it. And yet, we feel its pull. Everything around us is moving in its direction. Astronomers discovered its influence by tracing the peculiar velocities of thousands of galaxies. Their motions, when corrected for cosmic expansion, all seem to point toward a single area in the sky, an invisible gravitational sink. That was the Great Attractor. As technology improved, astronomers used infrared, radio, and X-ray observations to peer through the dust. What they found were hints of massive galaxy clusters, including the Norma cluster, a dense and rich collection of galaxies some 220 million light-years away. It became the leading candidate for the core of the Great Attractor. And yet, there was a problem. Norma is large, larger than average for a galaxy cluster, but not large enough. When scientists added up all its visible matter, even accounting for dark matter, it still fell short. It could not fully explain the speed with which galaxies were racing toward it. It was as if Norma itself was in motion, being pulled by something even more massive, hidden further beyond. The gravitational tug-of-war stretched across vast cosmic distances, and the Great Attractor began to look less like a final destination and more like a waypoint in a grander journey. Further out, nearly 650 million light-years from Earth, lies the Shapley Supercluster, named after astronomer Harlow Shapley, who first noted its presence in the early 20th century. It is one of the most massive known structures in the observable universe, a sprawling complex of galaxy clusters and filaments, packed so densely that it warps the motion of galaxies around it. When cosmologists included the mass of Shapley in their models, many of the discrepancies began to resolve. The flow of galaxies, including our own, was not just toward the Great Attractor. It was continuing beyond, toward Shapley itself. What this suggests is a kind of cosmic migration. Our galaxy, our group, and our supercluster are not stationary, nor are they circling in place. They are on a one-way path, caught in the gravitational currents created by the largest structures in the universe. The Great Attractor is real, but it is not alone. It is part of a chain of motion, shaped by gravitational wells we are only beginning to map. As data improves, and as surveys like cosmic flows expand, we see that what we once believed to be the center may in fact be just a bend in the river. These flows of motion, sometimes hundreds or even over 1,000 kilometers per second, paint a universe that is not just expanding, but streaming. Galaxies are like leaves on an invisible wind, carried not by chance, but by structure. The scaffolding of the cosmic web, laid down billions of years ago by gravity, dark matter, and the imprint of the Big Bang itself. The Great Attractor and the Shapley Supercluster are just the beginning. They are signs that our motion has direction, and that even on the grandest scales imaginable, the universe is still unfolding. As astronomers mapped more and more galaxies, the picture of our motion through the cosmos became clearer, but also more unsettling. We were not merely falling toward the Great Attractor, nor only toward the Shapley Supercluster. Something stranger appeared to be at work. In 2008, a team of scientists led by Alexander Kashlinsky used data from NASA's Wilkinson Microwave Anisotropy probe to study subtle shifts in the cosmic microwave background. What they found became known as dark flow, a mysterious, large-scale motion of galaxy clusters in the same direction, at speeds exceeding 1,000 kilometers per second. This flow extended beyond what could be explained by the gravitational pull of known structures like Laniakea or Shapley. It seemed to affect clusters hundreds of millions of light-years away, all heading in roughly the same direction, toward a patch of sky between the constellations Centaurus and Vela. But the strange part was not just the motion, it was the lack of explanation. There appeared to be no visible mass, no great attractor massive enough in that direction to justify the observed speeds. It was as though the entire region of the universe was being drawn towards something beyond the cosmic horizon. This raised profound questions. Was there something outside our observable universe? A superstructure? A vast overdensity? Or even a region with different physical laws, tugging on our portion of space? Or was this an artifact of measurement? The idea of dark flow remains controversial. Some studies, including data from the European Space Agency's Planck satellite, failed to find strong evidence to support it. Others argue that the signal is real, but its interpretation is still incomplete. Regardless of its status, the concept challenges our understanding of the universe's largest-scale behavior. It reminds us that there may be forces at work we have yet to fully comprehend. While dark flow represents a potential mystery beyond the limits of observation, there is another feature of the cosmos that reaches back into its earliest moments and leaves a more measurable imprint: Baryon Acoustic Oscillations, or BAO. These are not currents of galaxies or winds of gravity. They are frozen sound waves, relics from the time when the universe was just a few 100,000 years old. In that primordial plasma, waves of pressure rippled outward from dense regions, just like sound waves move through air. When the universe cooled and became transparent, these oscillations were frozen in place. The result was a series of density shells, subtle rings of slightly higher matter concentration that would later guide the formation of galaxies. Today, billions of years later, we can still detect these ancient patterns. They are written into the large-scale distribution of galaxies, visible as a faint statistical preference for galaxies to be separated by certain distances. Like ripples on a cosmic pond, they echo across space. In 2023, astronomers Brent Tully, Daniel Pomerade, and colleagues discovered that many of the largest known structures, the Sloan Great Wall, the Hercules Supercluster, and the Coma Cluster, appear to lie along the surface of a vast cosmic shell centered on a region known as the Bootes Supercluster. The shell spans over 400 million light-years in radius. The team believes this may be a single Baryon Acoustic Oscillation, still visible after billions of years, a structure born from sound in the early universe. They gave it a name inspired by Hawaiian cosmology, Ho'olelana, meaning, "From deep darkness came murmurs of awakening." It is a fitting phrase for a phenomenon that bridges the chasm between the dawn of time and the present-day cosmos. Through BAO, we glimpse not just motion, but memory. Waves that once shook the infant universe and now guide the movement of entire galaxies. These patterns give us a ruler to measure the expansion of the universe, a fingerprint of the moment when light and matter first separated, and a quiet reminder that even silence can leave an echo. Gravity is the great sculptor of the cosmos. It gathers gas into stars, stars into galaxies, galaxies into clusters. It builds walls, filaments, and superclusters. It gives the universe structure, and it has drawn the Milky Way toward the Great Attractor, then onward toward Shapley. For billions of years, gravity has ruled, but now that reign is ending. A new force is emerging, one that does not pull, but pushes, one that does not build, but unravels. That force is dark energy, and it is reshaping the fate of the universe. Dark energy is unlike anything we have encountered. It does not behave like matter or radiation. We cannot see it, touch it, or measure it directly. Yet we know it is there, because the expansion of the universe is accelerating. Galaxies are not just drifting apart. They are being driven away from each other faster and faster, as if propelled by an invisible wind. This acceleration cannot be explained by gravity. In fact, it works in the opposite direction. The best explanation we have is that empty space itself possesses energy, a property built into the fabric of space-time. And it is in the emptiest regions that dark energy does its greatest work. The voids, vast cavernous spaces between filaments of galaxies, are nearly empty of matter, but they are filled with dark energy. As the universe expands, these voids grow. They stretch, merge, and swallow up the surrounding cosmic structures. Their boundaries push outward, not because of any explosive force, but because dark energy is embedded in the vacuum itself. Where gravity pulls, dark energy pushes, and in the long run, that push is stronger. This is why, despite the pull of Laniakea, of Norma, of Shapley, our journey will not continue forever. The local group, our galactic neighborhood, will remain gravitationally bound. The Milky Way and Andromeda will merge. A few smaller galaxies will fall in. But that is where the story ends. We will never reach Virgo. We will never fall into the Great Attractor. The expansion driven by dark energy will stretch the fabric of space so fast and so relentlessly that even the strongest gravitational bonds beyond our local group will snap. In time, the universe will become a sea of isolated islands, each gravitationally self-contained, surrounded by emptiness. The great walls and filaments of the cosmic web will vanish beyond our cosmic horizon, receding faster than the speed of light. Even light from distant galaxies will one day no longer reach us, and what remains will be the lonely remnants, quiet galaxies drifting in silence, as dark energy steadily erases the large-scale structure of the cosmos. In a universe ruled by gravity, things come together. In a universe ruled by dark energy, everything falls apart. There was a time when matter ruled the universe. Galaxies pulled on one another, clusters grew heavier with age, and gravity guided the choreography of stars and systems. But that time has passed. Around 5 billion years ago, a cosmic shift occurred. The expansion of the universe, once slowing under the weight of its own gravity, began to accelerate. Something had changed. A new player had stepped onto the stage, silent, invisible, and immensely powerful. It was not matter. It was not light. It was something else entirely. Dark energy. This was not the first time dark energy appeared in the history of science. In the early 20th century, Albert Einstein had introduced a term called the cosmological constant into his equations, not because the math demanded it, but because he believed the universe should be static. But the universe refused to sit still. When Edwin Hubble discovered the expansion of space, Einstein reportedly called his constant the greatest blunder of his life. And yet, decades later, scientists realized that this forgotten term might be the key to understanding the most profound force in the cosmos. Today, dark energy is thought to make up nearly 70% of the total contents of the universe. It is not located in any particular place. It does not cluster or form objects. Instead, it exists everywhere, woven into the vacuum of space itself. And the more the universe expands, the more dark energy there is. As galaxies drift apart, the space between them grows, and with it, the influence of dark energy multiplies. It is a feedback loop with no end, a cosmic runaway effect. Matter spreads out, gravity weakens, and dark energy tightens its grip. This is the turning point of the universe. In the past, gravity sculpted the cosmic web. Galaxies, filaments, and clusters, all assembled slowly over billions of years. But now, those threads are beginning to unravel. The pull of gravity is no longer enough to hold the largest structures together. Superclusters will disperse. Cosmic flows will stall. The majestic migration toward the Great Attractor will come to a halt and begin to reverse. Over the next tens of billions of years, the universe will slide into a new era, an era of isolation, quiet, and ever-accelerating expansion. And this is what dark energy has brought us. Not destruction, but dissolution. A slow, unstoppable fading of the cosmos. Not with a bang, but with a drift. In the far future, the galaxies we see today will vanish from view, carried beyond our reach by space itself. The sky will grow dark, not because the stars have died, but because their light can no longer find us. The universe, once a place of brilliant structure and connection, will become a cold and silent sea of expanding nothingness. This is not the end of motion. It is its final consequence. The story of the cosmos is a story of motion, galaxies spinning, stars orbiting, clusters collapsing under gravity's pull. But motion is not eternal. In a universe dominated by dark energy, even the most majestic trajectories must eventually end. Already, the expansion of space is accelerating, driving galaxies apart faster than light can bridge the distance. In time, that expansion will isolate every gravitationally bound system. And so begins the long descent, the era of cosmic isolation, a time when even light can no longer find its way between the stars. The local group, once a loose collection of galaxies, will by then have merged into a single giant elliptical system, Milkomeda. All of its member galaxies, Milky Way, Andromeda, Triangulum, and dozens of dwarfs, will have coalesced under gravity. No new galaxies will join. Nothing will enter. It will be a closed system, marooned in the expanding void. Outside, the rest of the universe will continue to rush away. The Virgo cluster will recede beyond the observable horizon. Shapley, Laniakea, and the Great Attractor, all lost, not because they vanished, but because their light can no longer reach us. Inside Milkomeda, the stars will remain for a while, orbiting in chaotic paths. But over billions of years, gravitational interactions will scatter them. Some will fall into the galactic core, consumed by the central black hole. Others will be ejected into intergalactic space, forever severed from their home. New stars will no longer form. Milkomeda's reservoirs of gas will have long since been exhausted in the great starbursts following its formation. What remains will be a dwindling population of long-lived, dim red dwarf stars cooling slowly in the dark. As time stretches into the tens, then hundreds of billions of years, those red dwarfs too will die. Their cores will cool. Their light will fade. The galaxy will grow darker, star by star, until all that remains are stellar remnants, white dwarfs, neutron stars, and black holes. Milkomeda will become a graveyard of celestial corpses, each one silent, inert, and drifting. There will be no more light, no more fusion, no more birth. Just cold matter, suspended in the vacuum of a universe that no longer remembers what it once was. Beyond that, over unimaginable timescales, even these remnants will not remain. Through rare but inevitable interactions, black holes will slowly consume the last of their neighbors. Then, through a process called Hawking radiation, those black holes will evaporate, first the smallest, then the largest, over trillions upon trillions of years. The final black hole will vanish with a whisper, releasing the last particle of warmth into a universe now colder than any void we can imagine. What remains is a sea of subatomic particles, stretched thin across an ever-growing expanse. And then, silence. No galaxies, no stars, no structure, no observers to witness the end. Just emptiness, expanding without limit. The universe will not collapse into fire, nor freeze in a static shell. It will fade, infinitely, into featureless darkness. The story that began with a bang ends not with a crash, but with a whisper. And in that final stillness, motion itself ceases to have meaning. The cosmos, once alive with dance and fury, comes to rest. From the smallest atoms to the largest superclusters, from the first whisper of the Big Bang to the long drift into cosmic darkness, the universe has always been in motion. Motion is not a side effect. It is the essence of existence. Every structure we see, every star that shines, every planet that forms, every breath we take, is part of a journey written in gravity, time, and light. We once believed we were the still point in a turning cosmos, but now we know better. We are not fixed. We are passengers on a vast, invisible current, a current that began long before us and will continue long after. It has carried us from the cradle of our galaxy toward the unknown, through collision and creation, through attraction and isolation. And perhaps, in the face of such overwhelming scale, the most human thing we can do is to listen, to the murmurs of ancient light, to the quiet pull of unseen forces, and to know that even in the stillness, we are always moving. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.